Welcome, everybody. It's very nice to have you here at the IST Colloquia, and this is the first online Colloquia. So we maybe have some, hopefully don't have many bugs to work out, but we'll see. So far, so good. And it's my pleasure to introduce to you Andrea Liu. So Andrea did her bachelor's degree at UC Berkeley, and after that, she did her PhD in physics at Cornell University with Michael Fisher. She then did 2 postdocs, first at Exxon Research, and then after that at UC Santa Barbara. In 1993, she started as an assistant professor at UCLA, where she worked for about 10 years. And then in 2004, she joined the University of Pennsylvania, where she currently holds the Hepburn Professor of Physics. Andrea is the recipient of numerous awards and accolades, including a Fellow of the National Academy of Sciences, a Fellow of the American Physical Society, and the American Association for Arts and Sciences. And I think it's fair to say that her group is recognized as one of the top soft matter theory groups in the world, especially on the topic of disordered materials and jamming. And so I'm very excited to have Andrea here. I think Carl as well, Carl Goodrich, as Andrea was his PhD advisor. And we're really looking forward to what you have to say. I should mention to everyone that I've been pointing out that there is an option on the bottom of your screen in the center to raise your hand. And Andrea has told me it's okay for you to ask questions during the talk, and of course there will be time for questions after the talk. So if you have questions during the talk, just raise your hand, and if Andrea sees it, she'll get to you. So without further ado, thank you very much for agreeing to share your work with us, Andrea, and we're looking forward to what you have to say.
Okay, thanks very much. Yeah, I would really love it actually if you would raise your hand for questions during my talk, because I can't really see all of you, and that will just reassure me that you're not asleep, or not all of you are asleep. Okay, so thanks very much for this opportunity to speak. I have to say I was really looking forward to visiting Vienna, and you know, seeing where Schubert and Beethoven and Mozart and Mahler and many others, Schoenberg, all were working. But I will hope to visit it at a later time. So what I'm going to talk about today is something that I'm very excited. This is sort of the main theme of my research nowadays is really to think about how to go beyond this traditional ways of doing statistical mechanics to handle systems that we can't ordinarily tackle with statistical mechanics. And today I'm going to focus on one example, which is the glass transition. So on the left, you see a molten glass, right? On the right, you see glass vessels. These date from Roman times. So we've actually been making glass for the oldest glass vessels, you know, probably about 3,000 years ago. Were made 3,000 years ago. So we've been using the glass transition for a long time, but it still remains somewhat challenging to understand. And so I'm going to talk about the ways that we're using machine learning to look at that. Oh, great. Now, why is this? Oh, I just clicked my mouse. Okay. So let me just remind you, why do we all take statistical mechanics, right? And the reason why we do is sort of summed up by Helen Keller, actually. Alone we can do so little, together we can do so much. So we want to understand, the idea is to understand the collective properties of many body systems from microscopic properties. So how does physics at the microscopic scale, for example, at the level of copper atoms and their interactions, lead a copper wire to sometimes be conducting and sometimes be superconducting at the collective macroscopic scale? Or if you start out with rod-like molecules here, liquid crystal molecules, how can you make liquid crystal displays? Or how do you get the collective behavior that makes liquid crystal displays possible? And of course, there's the classic example of, phase diagrams, phase behavior, and critical points, all these phase transitions that we have understood beautifully using statistical mechanics. And that's the whole goal of condensed matter physics, right? Is to gain this microscopic understanding of collective behavior in many body systems. And when you think about what statistical mechanics does, it does several things. So first of all, it solves the TMI, or too much information problem, right? And that is, you start with all the microstate information. That's a huge amount of information. And you reduce it down. And so, for example, if you're thinking about a classical statistical mechanics system, you start out with positions, the velocities of all your particles, for example, in a glassy liquid. And then the idea of statistical mechanics is that you boil this down to distributions, which you can characterize just often by the average and variance of microscopic quantities. Okay. The other thing it does is it tells you, we use it to identify what are the right microscopic quantities to look at. The microscopic quantities whose distributions tell us about what's happening at the macroscopic scale. Okay. So first we have to reduce all that microscopic information and capture it in terms of the right microscopic quantities. Okay. But there are lots of problems where statistical mechanics has failed, or at least has not given us as much as we would like. Okay. And so examples of these are ones that have preoccupied me for a long time. With my collaborator, Sid Nagel at the University of Chicago. So for example, if you start out with silicon oxygen atoms to make silica glass, or you could start out, or you could have systems where you have grains of sand, which are usually actually glass beads, so they're spherical, okay, which, you pour them in. You can pour them and they behave like a liquid, or if you walk on the beach, you don't sink through as you would sink through a liquid, but it actually supports your weight like a solid. Or you could have bubbles, spherical bubbles alone at the microscopic scale, which you put into a foam together, many of them into a foam, and you can either smear it around, it behaves like a liquid, or it can sit on your hand and jiggle like a solid. Okay, so these are all systems that show macroscopic collective behavior that's rather similar to the liquids and solids that we see all the time and have handled through statistical mechanics. And they have resisted full solution by statistical mechanics for several reasons. First of all, they're far from equilibrium, right? Obviously, a system of grains is far from equilibrium. It's not in thermal equilibrium. When you're pouring it, you are actually, perturbing it. Okay, and that is why it is flowing. So it is out of equilibrium. I'll talk about how the glass problem is out of equilibrium as well in a little bit. Okay, these systems are naturally disordered. That means they're lacking crystal symmetries and other kinds of symmetries that we've relied on in order to understand what's going on. And they often show nonlinear response. So the foam, for example, if you're not shearing it, it just sits on your hand like a solid. If you smear it hard enough, right, it flows like a liquid. And that's a nonlinear response. And again, statistical mechanics has worked well when it's in equilibrium or near equilibrium and in linear response, but it's not so great at handling nonlinear response. So I'm going to zero in today on the glass transition. Oh, here it says earliest glass making is 3000 BC, so it's actually 5,000 years. So we've been making it. Okay, so what is the glass transition? So the idea is you take a liquid, right? You cool it through the glass transition. And if you cool it extremely slowly, right? What happens is that it'll tend to crystallize. But if you cool it fast enough so that you can't form nuclei of the crystals, the crystal nuclei, okay, then you don't crystallize. And as you keep cooling it, what you find is that it remains a liquid. The particles remain in a disordered structure, okay? But the time that it takes to equilibrate the system, to reach thermal equilibrium, which we call the stress relaxation time, or simply the relaxation time, increases continuously. Not only continuously, it increases dramatically. So for many, many classes, you can actually get a 10 orders of magnitude increase in just tens of Kelvin, okay? So the relaxation time is just shooting up incredibly rapidly. Once it shoots up that rapidly, right, it becomes very hard to equilibrate it. And so when a system doesn't equilibrate on a reasonable timescale for waiting, that's what we call a glass. And this is a generic feature. As long as you can avoid crystallization, you will always see this behavior in every system, okay? And the interesting thing, right, if you looked at a snapshot of the glass and compared to a snapshot of liquid, you would not be able to tell which is which. So now comes the question, right? How does the stress relax? How does the system reach equilibrium? Well, in order for a system to reach equilibrium in a liquid, what's happening is that the particles of the liquid, the constituent particles, are rearranging all the time, okay? And any particle can rearrange at any time. If I think about solids, it's very different. So crystals, for example, in crystals, not all particles are equally likely to rearrange. The ones that are at defects, such as dislocations or grain boundaries, are far, far more likely to rearrange, okay? And so this has been a question in glasses and glassy liquids. And in fact, we can understand a lot of the properties of crystals, okay, in terms of, you know, what is happening at these defects, okay, the responses. And so for glasses and liquids that are above the glass transition, but glassy, the question is, can we figure out which particles are likely to rearrange? Which ones are at defects, like the ones we see in crystals, except that the structure is disordered, right? So in a sense, you would say everything is a defect in the normal sense, but maybe there are certain particles that are more likely to rearrange than others, which define a new class of defects for glasses. So that's been an over 50-year-old challenge, okay, is to find such particles from structure. And people had basically, by 2010, sort of given up on this, okay? And some of the reasons is that as you cool down the liquid approaching the glass transition, the structure changes only a tiny little bit. They're only subtle structural changes, and they are continuous, okay? Whereas the dynamics changes a huge amount, okay? No one had been able to find a structural signature of the glass transition or of kinetic heterogeneities. I'll tell you what those are in a bit. So people had sort of given up, but it turns out that it's really easy to identify these with machine learning, okay? And that's where we started. So that was our initial question. Could we just find these defects in the supercooled liquid, okay, a liquid just above its glass transition? Could we find which particles were much more likely to rearrange than others? And what sets machine learning apart from the traditional physics thing is that usually in physics you say, okay, I know I'm going to come up with a quantity that really encapsulates the right physics, and then I'm going to see if that quantity predicts rearrangements. And none of these things worked very well, okay? And the whole idea of machine learning is you say, I'm not going to think so hard, okay? I'm not going to just use one quantity to characterize the structure. I'm going to use many of them. Each of them may not be that illuminating in itself, okay? But if I use enough of them, maybe I can figure it out, okay? And then the idea is you take some of your data. For example, this could be from a molecular dynamics simulation, okay? Or it could be from an experiment, and we've done both, okay? So you use a small subset of that data to infer, in our case, we infer the linear combination of those quantities that correlates most strongly with particle rearrangements. And then afterwards you can say, let me look at that linear combination and what was the physics that is in that linear combination, and let me get the physical intuition afterwards, okay? So it's sort of backwards from the usual physics way of doing it. So what structural quantities did we use? Okay, we're going to use many of them. In fact, let's say we use m different quantities where m is of order 100. Okay, and what we chose to use was basically the pair correlation function at different distances from my particles. So for each particle, I look and I say, how many neighbors do I have at this radius? Okay. How many neighbors do I have at that radius? Whose centers are at that radius, and so forth. And this is a way of characterizing the local structure of its neighborhood, okay? And then, how do we do this? The idea is if we have m of these quantities, g of r, for example, at m different values of r, we construct an m-dimensional vector, okay, whose components are the values of g of r different r. In other words, we let one axis, we construct an m-dimensional space where one axis is g of r at one value of r, another axis represents g of r at the second value of r, etc., okay? And then the actual values of the local g of r for this particle, okay, are a point in this high-dimensional space. So, so now I'm representing this high-dimensional space, which of course I draw in 2 dimensions, because that's all I can draw, okay? And so each point represents the structural environment, the local structural environment of a particle, okay, in this space. And now I take a bunch of particles, this is called my training set, for example, from my molecular dynamics simulations, and I take a subset of these particles and I choose my subset to contain particles that are just about to rearrange. I color those points white, okay? And then I have particles that haven't rearranged for as long as the relaxation time tau. I color those points gray, okay? Now the idea is in this m-dimensional space, I'm gonna construct an m-1 dimensional plane that best separates these 2 classes of points, okay? And then we're going to construct a scalar variable. So now if I take another particle and calculate its structural environment, that's a new point here, I can calculate where that point is relative to that hyperplane, okay? And the magnitude of its difference from the hyperplane, okay, and the sign both come into it. So if it's on the non-rearranging side of the hyperplane, it has a negative sign, okay, and the distance is its magnitude. And if it's on the rearranging side of the hyperplane, it has a positive sign, okay? So the softness is the sign distance of a particle's environment from that hyperplane. So that is now, what we're saying is, okay, that is a structural variable. It is a static structural variable that just characterizes the local structural environment of a particle, okay? But it's been trained on rearranging particles versus non-rearranging, so to distinguish that, okay? So it's that hyperplane that contains the physics, that tells you the connection between structure and dynamics, okay? The nice thing is that all we needed to know were the particle positions as a function of time. We don't actually need to know the interactions, okay? And that's really good for experiments. So we've been able to apply this to a number of experimental systems because you never precisely know their interactions. And this allows us to do this without needing to know them. Okay. And you can have friction, you can have all these things, and you can still train your hyperplane. It does mean, though, that the hyperplane is different for every different system. For every system, you need to train again. Okay. All right, so it does work. So let me just point out that in the continuum limit, where we have not m different values of r, but an infinite number of different values of r, the softness just turns out to be a weighted integral over the local pair correlation function for particle I. Right?
Could I ask a question?
Yes, sorry.
Could you move back a tiny bit?
Yes.
A few slides, 2 or 3.
Let's see, how to go back. Yes, I can go back.
Yeah, you had these balls which were increasing in size. Certain colored circles, yes, here. I mean,
yes.
Could you explain what the difference between this and alpha shapes is?
And what?
And alpha shapes.
Alpha shapes. Ooh, I'm sorry, I don't know what alpha shapes are. So,
all right.
Let me just say what we're doing. Okay. So for the blue circle, okay, we just say how many particle centers are on the blue circle, are in this blue little thin ring. Okay, happens to be 0. Okay. How many particle centers are in the red ring? How many particle centers are in the green ring, etc. So we're just counting the number of particle centers in the ring divided by the area of the ring.
All right, so you take the alpha shape and then you do a counting on the number of connected edges.
Okay, I'm not sure what alpha shape is. I mean,
are you familiar by any chance of with the work of Hiraoka? Yes, sorry, I'm not very good at pronouncing Chinese names, but Yusaki Hiraoka about topological data analysis.
Okay, no, okay, because what you were saying did sound like a little bit like what we do at persistent homology. We're not doing that. We actually have done things like that. Oh, you're talking about alpha, alpha complexes. Okay, so we're not doing that here. We have actually done that as well. That's another way that we can characterize the structure. So we can say, okay, I characterize my points and then I grow some. I allow each particle has a point associated with the center, and I draw a little circle around it, and then I draw the circles and I see when the circles start to overlap and so forth. We're not doing that, but this is somewhat related. This is a more liquid state approach. This is how you would do liquid state theory for liquids. Okay, you would express things in terms of the pair correlation function. But yes, we have done it. We have done it with alpha complexes too. We have a paper. Oh no, we haven't posted it on the archive yet because we haven't submitted it yet. It's almost there.
All right.
Where we do that. Okay. It's another way to train things, and it's a perfectly good way to to characterize your structure as well. Okay, that's just not what we did here.
All right, but it does seem related.
Yes, it is related.
Many thanks.
Yeah. Okay. And we have used different machine learning methods to do this. This is what we use, this thing of constructing the hyperplane, that's called a support vector machine. We've also used neural networks, unsupervised learning, linear regression. We've used a bunch of different things. Okay. All right. So, so what this amounts to, though, in the continuum limit is just that softness is this weighted integral of the local pair correlation function, where the weights have been chosen. The weights basically are the hyperplane, are related to the hyperplane, and they've been chosen so the softness correlates most strongly with rearrangements. And it works. Okay, so I'm going to show you this movie. Okay, so this is a movie, the MD simulation of a Leonard-Jones mixture. Okay, and the red particles are on the rearranging side of the hyperplane, positive softness. The blue particles have negative softness, okay? This is above the glass transition, but not very far above it. And now it peels away only to look at the particles that are rearranging, and you see that 90% of them have positive softness, are red, okay? So it really does work. We are really very successfully able to identify which particles are likely to rearrange. Okay, so what is softness? Okay, as I told you, it is weighted integral to local G of R. But if I look, I can just look at soft particles and look at their average pair correlation function. That's the red, and I can compare it to the pair correlation of on average. Okay, this is for a mixture of two size particles, A and B. Okay, and what you see is the red and the black, the soft particles, and the particles as a whole, all of the particles, have very, very similar pair correlation functions. Okay, but the softer ones do have lower peaks and higher valleys. And what that means, and this comes back to the old idea of a cage, that the particle in a glassy system has to escape from a cage of its neighbors. This is a way of quantifying the cage. So softness gives you that. Okay. So now, though, it's like, this is a really subtle difference of the pair correlation function. And you might ask, does the pair correlation actually contain enough information to tell us anything about the glass transition? And several years ago, actually, there was a paper by Berthier and Tarjus that said, no, that's not enough. Okay, and they took this example, which is a Leonard-Jones glass, and what's called the Weeks-Chandler-Anderson potential, which is the same as the Leonard-Jones. You just cut it off at the minimum and shift it up so that it only has the repulsions. It doesn't have the attractions. The whole idea of the theory of liquids is that the attractions sort of act as a perturbation, but the repulsions are really telling the story. Okay, and that is reflected in G of R. G of R is extremely similar for these two systems, as the theory of liquids would say should be. Okay, the repulsions make almost no difference to the pair correlation function. And yet, if you look at their dynamics, it's totally different. So this is the relaxation time, tau. I'm sorry, sometimes I call it tau alpha and sometimes I call it tau, but they're the same thing. Okay, so the relaxation time tau for the Leonard-Jones system looks like this as a function. This is plotted log of tau versus 1 over temperature. Okay, it shoots up. That's the blue one. And the system with only repulsions has a much, much more gradual increase of the relaxation time. So this tiny difference in the pair correlation function gives rise to a huge difference in relaxation time. So is that enough? Well, remember that softness, right, is this weighted integral over the correlation function. So the average softness is a weighted integral of the average pair correlation function, which, and this is a tiny difference, right? And that's comparable, this sort of tiny difference that we see between soft particles and average particles, particles with positive softness versus the average. So here is the average softness. And what you see is, yeah, the average softness is definitely different. For the system, the red system was with only repulsions, and the blue system is the Leonard-Jones. But if I look at the relaxation time, which were so different when I looked at them as a function of 1 over temperature, if I look at them as a function of the average softness for the two systems, they're nearly on top of each other. Okay, so yes, that small difference in the pair correlation function actually leads to a big difference in the average softness, and that leads to even bigger differences in differences in the relaxation time. But the relaxation time as a function of the average softness is the same, or nearly the same, for the two systems. So that gives us hope, right? That we can actually do what we want to do, because what we want to understand, remember, the softness is a microscopic quantity. It characterizes the local structure around a particle. And so the average softness is a property of the distribution of these microscopic quantities, whereas the relaxation time is a collective quantity, a macroscopic collective quantity. So can we use this to try to understand the connection between the average softness and the relaxation time, which is, of course, our goal as people who do statistical mechanics. So the relaxation time is only one of several things that we want to understand. But let me just sort of tell you about what the relaxation time typically does in a glassy system. So this is a plot of viscosity, but it just tracks relaxation time. So you can read it as a plot of the log of relaxation time versus one of the temperature, similar to what I showed you before. Okay. So a straight line on this would be Arrhenius behavior, which means that the relaxation time just goes like e to the sum energy barrier over temperature, and that energy barrier is well defined. It's a constant. Okay. So that would be a straight line on this plot. And you can see that different glassy systems have very different shapes of this curve. So some of them are pretty straight. Those are called strong glass formers. And those are network glasses like silica, okay? Like what makes our windows are the vases that I showed you earlier. Then there are fragile glass formers, okay, where the relaxation time rises much more rapidly than you would expect based on the Arrhenius rule, okay? And Leonard-Jones is an example of that, but glycerol, lots of liquids are strongly super Arrhenius, so this is called super Arrhenius. It's faster than Arrhenius as you lower the temperature. Okay. All right. So if we look at this, if we look at the behavior, for example, of the Leonard-Jones system, okay, then if you look at the relaxation time, you can write it as e to some energy barrier over temperature. And what you see is that at high temperatures, it's constant, okay? Which means you see Arrhenius behavior. But as you go below some characteristic temperature called the onset temperature, that apparent energy barrier, okay? So this is the log of the relaxation time versus temperature. Now relaxation, that energy barrier, or rather T times the log of the relaxation time is the energy barrier. That increases, okay, as you go to lower and lower temperatures below this onset temperature. And the fact that that's increasing means that it's super Arrhenius. If it were decreasing, it would be sub-Arrhenius. Okay, but it's increasing, so that's rising faster than you would expect based on the Arrhenius law. Okay. It's interesting that if you look at how some stress relaxes as a function of time. So apply some stress, watch it relax as the system equilibrates, okay? You can fit it to a stretch exponential function, okay? Where the stretching exponent is 1. In other words, it's just purely exponential at high temperatures, but once you get below some characteristic temperature, which is the same temperature, by the way, that we saw where the energy barrier started going up, T0, this onset temperature, the stretching exponent starts to decrease, okay? So the relaxation time becomes less and less exponential, more stretched as you lower the temperature below that onset temperature. There's yet another feature which is called a kinetic heterogeneity, which becomes more and more pronounced as you lower the temperature. So, so if you look at how far a given particle moves within the time of a relaxation time, okay, then it turns out that some particles don't move at all, whereas other particles move a long way. And you've seen this before we all went into lockdown, okay? Sometimes we get stuck in traffic jams, and as the traffic is approaching the onset of jamming, right, it turns out that the cars in the next lane are always going. They have high mobilities. In a given interval of time, they go a long way, whereas you are stuck, okay? And that is a kinetic heterogeneity. It's actually very similar physics to what happens in a glass glassy system. And this is on the right is just a movie of a granular system. This is actually an experiment where the particles tracks are shown, and they are labeled according to, by color, according to how far they moved in the relaxation time. So red is far and blue is not far. Okay, so the red tracks are long and the blue tracks are very short. So that's an example of this kinetic heterogeneity. So that distribution of how far they move becomes very non-Gaussian, broader as you lower the temperature, but it is Gaussian above the onset temperature, okay? So the dynamics are homogeneous above the onset temperature. They become heterogeneous below the onset temperature. All right. So these are the things that I'm going to go through, okay, to connect microscopic softness to glassy phenomena. These are things that it's exactly the relaxation time, the form of the relaxation with time, which is exponential above the onset temperature, stretch exponential below, the behavior of the relaxation time, which becomes super Arrhenius below, and the dynamics, which becomes spatially heterogeneous. And then below the glass transition, right, things fall out of equilibrium, and now the relaxation time depends on how long you wait as the system is trying to reach equilibrium. All right, so first I'm going to concentrate on this onset temperature. So what I'm going to plot, what I'm going to calculate is for particles of a given softness, okay, I look at which fraction, what fraction of them are rearranging at a given time, okay? And then look at this on average. So for particles of softness S, what fraction of them are rearranging? I call this the probability of rearranging, okay? And what we can do is we can plot the probability that a particle is rearranging, okay, for a fixed softness as a function of 1 over the temperature. So I plot the log of this as a function of 1 over temperature. What you see is that it is a straight line, okay? So if I just plot the probability that it's rearranging, that's not Arrhenius at all, okay? But Arrhenius behavior is a straight line here, and what you see is that for particles of a given softness, the behavior is Arrhenius. It looks like this. And that means there's a well-defined energy barrier for particles of a given softness. But what you can see is soft particles, okay, have different slopes here. So these different colors represent softnesses going from highly positive, highly negative. And this is the energy barrier that you can extract from this. And what you see is that softer particles of high positive softness have low energy barriers to rearrange, while particles with negative softness have high energy barriers to rearrange. And that says that as I wait in temperature, right, softer particles are much more likely to rearrange. Okay, so, and this is actually heterogeneous dynamics, right? Because different particles have different softnesses, and ones that have high positive softness are likely to rearrange, whereas ones that have very negative softness don't rearrange, and so don't go anywhere. Okay, so that's the kinetic heterogeneity. But what does that have to do? And this property that the probability of rearranging at a given softness is Arrhenius appears to be generally true. So this is the Leonard-Jones mixture. I just showed you that. We also looked at a strong glass former, silica, network glass, okay? And that, again, the probability of rearranging as a function of log of that versus 1 over temperature, straight line, so this is Arrhenius too, okay?
Andrea,
these are systems that have nearly Arrhenius behavior.
Andrea, can I ask a question?
Yeah.
The last graph you showed, that was silica from like an MD simulation, or?
This is MD simulation. It's the BKS model of silica.
Okay, okay.
This is from a simulation.
Okay, thanks.
Yes. We've looked at simulations of the thermalized vertex model of epithelial tissues. Okay, it's interesting from this point of view because it shows sub-Arrhenius behavior, and again, in that case, so it increases slower than Arrhenius. In that case, again, we see the probability of rearranging as Arrhenius for particles of given softness. And even crystalline systems. So these are aluminum polycrystals. Okay, we can look at the probability of rearranging as a function of softness. It turns out soft particles live in grain boundaries, dislocations, as you would expect, and And the probability of rearranging is, again, Arrhenius in temperature. So we see this Arrhenius behavior of the probability of rearranging across the whole range from sub-Arrhenius to Arrhenius to super-Arrhenius behavior, so the range of fragile to strong glasses, and across the whole range of order to disorder, so crystalline to glassy. And of course, the whole softness idea works across this whole these ranges as well. All right, so now I've got these energy barriers. What are the consequences of that? So if I look at the energy barrier and this what we call entropy, okay, but it's this other piece here, the temperature independent piece in the probability. These are both linear in softness. And what are the consequences? Well, if I rewrite these and turn these linear coefficients, okay, what you see is you can rearrange the probability of rearranging to a piece here that doesn't depend on softness. It's purely Arrhenius, okay? And a second piece, which depends on structure, depends on softness here, okay? But there's one temperature here where this prefactor can be 0. But that prefactor, the probability of rearranging doesn't depend on softness, okay? That onset temperature is S1 over E1, okay? And if I go back and look at that, so below this temperature, then this is where the dynamics start to become dependent on softness, okay? And if I look at that, I see, yeah, there is a place where all these curves cross. That's where the probability of rearranging doesn't depend on the softness, okay? I'm going to call that the onset temperature. That's S1 over E1, okay? And I'm going to compare that to the onset temperature that people have measured for example, when the energy barrier starts to increase. The things where I showed it was constant at first and then started to increase below the onset temperature, or get it from the kinetic heterogeneities. And this is plotting our onset temperature versus the previously measured thing based on the phenomena, and they are the same. Okay, the dotted line is equality of the two. Okay, so we have predicted the onset temperature. That's a collective quantity. Okay, and it's below that the dynamics start to become dependent on softness. That's where the system becomes a glassy liquid instead of an ordinary liquid. All right, so that's what I've explained so far. Okay, that worked. Okay, let's go on to the next thing, which is this thing about the relaxation time. Can we understand that behavior of the relaxation time, whether it's Arrhenius or super Arrhenius or what? To do this, we're going to look at aging. So we're going to take the system, we're going to quench the temperature from above the glass transition to below, okay? And now, when we're below it, we can't equilibrate. We can't wait long enough to equilibrate. But the system does evolve with time. So what I'm showing you is the softness of the particles. So red and opaque is high positive softness, black and transparent is high negative softness, okay? And what you see is over time, this system becomes darker and darker. It becomes, the average softness decreases as the system ages, as you wait, okay? So this is the waiting time after the quench. And because the system's out of equilibrium, the properties depend on the preparation history. When did I quench it? Where did I quench it to? And not just on the state variables, what's the temperature, where did I quench it from? And not just the state variables, you know, what is the temperature and pressure I'm at now? Okay. And what happens is that as you follow these things in time for different starting temperatures, okay, different ending temperatures of my quench, okay, I can plot the relaxation time and it changes with time, okay? And similarly, the average softness, as I showed you, decreases with time. Now, I can now plot and I can look at the probability of rearranging a given softness even as I'm out of equilibrium. And what you see is it falls exactly on the same lines that we have below. And so at different ages, the probability of rearranging a given softness is the same for a given as a function of softness as it was before. So what that tells you is that as you age, the system is falling into deeper and deeper minima the energy barrier is increasing, okay? But for particles of given softness, the energy barrier is the same as it was before in equilibrium. And the reason why the energy barriers increase with time is because the average softness is decreasing, okay? So, so what that's saying is that what's happening with aging is that the structure is changing, but the relation between the structure and dynamics is the same. So that aging is really a structural phenomenon. So if I do this, I can plot the relaxation time as a function of the average softness. And for different temperatures that I quench to, okay, I get different dependencies. So the log of the relaxation time is approximately linear in the average softness, and different temperatures that I quench to, I have different slopes, okay? And if I look at the equation that I have for the probability of rearranging as a function of softness, which I showed you before, and now I just make a simple assumption. I just say the relaxation time is 1 over the probability of rearranging evaluated at the average softness at that temperature. Then I get an expression that looks like this. It's e to the average softness times 1 over T0 minus 1 over the onset temperature minus 1 over the temperature. So that says that the log of the relaxation time should be linear in the softness with a slope, which is 1 over the onset temperature minus 1, the temperature that I quench to. And that's what I've plotted here, okay? And this is the actual slope that I got from these curves, and it works beautifully, okay? So what that says is that indeed, I can get the relaxation time from the probability of rearranging softness. And this works for Leonard-Jones, it works for the Weeks-Chandler-Anderson potential. It works for silica, okay? Okay, sorry. I can do the same thing for silica. This is the diffusion coefficient, which I say the diffusion coefficient is like the inverse relaxation time. So it's the probability of rearranging at the average softness. The points are the measured values for the diffusion constant from the simulation, and the curve is what we get from our prediction. It really works. Okay, so that works. So the last thing I want to talk about, how am I doing on time, is that the relaxation is exponential above the onset temperature. It becomes stretched exponential below, as I showed you before. Can we understand that? So one way to measure that is to look at what's called the overlap function. So I look at all of the particles and I say, if they've rearranged, if their displacement in a given interval of time is bigger than some amount, A, which is typically like half the particle size, okay, then they don't contribute anything. But if they haven't moved, then it's 1. Okay, so this just counts the fraction of particles that haven't moved in a given interval of time. Okay, and so when that time is 0, none of them have moved, and as time goes on, it just gradually decays to 0. Okay, and it decays non-exponentially. And you can see already, I have a distribution of softness values. Each one relaxes at a different rate because it has different probability of rearranging. Okay, so that's going to give you non-exponential relaxation. But I can do better than that. I can say, okay, what is the shape of that? So suppose now I just say each particle has a softness, and I just have these Arrhenius processes because the probability of rearranging is Arrhenius, and at each softness, they just evolve independently. Each particle just evolves independently with its Arrhenius relation given by its softness. That gives me the dashed lines. It's not too good, okay, compared to what we actually measure, which are the solid curves here. Okay, so it doesn't really capture the late time relaxation. But now, just you can make the following simple observation, which is that even for particles that don't rearrange, okay, their softness changes with time. Why? Because other particles nearby can rearrange, and that changes the local neighborhood, the local G of R, the pair correlation function for this particle, the structural environment of this particle. And what happens is that if you start with a delta function at a softness of particles, only look at particles of given softness at 0 times 0 and see how their softness evolves in time. Over time, that distribution will revert to the mean. And it is Gaussian. It's very close to Gaussian, and it spreads out in time, much like a diffusion process. That actually does quite well in describing this. And so we can just put in that physics, okay? That's called facilitation, by the way. So a particle that wasn't soft can become soft because a particle nearby rearranges, okay? We put that in, that gives these dashed lines, okay? Put in that physics, and that does much better, okay? So we not only see that the relaxation is non-exponential, but we have a decent theory for the shape of that non-exponential relaxation. So I hope I've shown you, okay? Before we had statistical mechanics, right? It's done beautifully for over a century to solve both the dimensional reduction problem, the TMI problem, and to find the right microscopic variables to give us a bridge between the microscopic and the macroscopic scales. Machine learning is, the whole point of machine learning is that it does dimensional reduction really well, okay? That's what machine learning is for, okay? So it's a natural thing to use to try to understand, to do statistical mechanics on systems where, you know, we can't do statistical mechanics in the usual way. What I've shown you also is that it is also designed to find very subtle correlations, right? The ability to recognize one face from another, distinguish one face from another, is also really great at finding out what distinguish particles that are likely to rearrange from particles that are not likely to rearrange, okay? And so, you know, this is where our ability as physicists comes in. We have to find what is the right microscopic quantity that is going to tell us about the macroscopic collective phenomena of interest. And in this case, what we did was we found the microscopic structural quantity, softness, that is correlated with dynamics, and that gives us a very promising basis for a theory of glassy dynamics. Just want to say, where are we going? And, you know, why am I so excited about this? Because it's not only traditional systems that are disordered and like glassy systems, disordered, non-equilibrium, you know, nonlinear response and so forth, that this is good for. It's even better, I think, for problems that are just totally resistant to statistical mechanics, biological systems. So the thing about biological systems is that every constituent can be different. Not only that, constituents can change over time as systems evolve. So for example, suppose you have cells in a tissue, then as the system is undergoing development, the properties of the cells are changing. The way they're interacting with each other is changing. And different cells have different properties, right? And so these are systems that we really can't handle. Not only that, not only are they changing, but they're not disordered, okay? They are designed by evolution to have very particular properties, and you can't treat it as just some disorder average, okay? So we're in this position now where there's a lot of data now available for biological systems. And of course, for big data analysis, you need big data, you need lots of data, right? But even the amount that we can collect for systems is not always enough. And the reason why is because statistical mechanics tells us that we need ensembles. So if we have systems that have different constituents by design or by evolution, we need ensembles of all the different outcomes of evolution, okay, possible outcomes from evolution, and we don't have that many. We may have different proteins that you have the same role across species, and then I have all those at my disposal. Well, that's still not very many. And what I want to say, and I wanted to mention this because this is work that came out of some beautiful stuff that Carl Goodrich did when he was at Penn as a graduate student, is that what we found is that in order to get ensembles, we actually need to design systems to have that function on the computer, okay? Then we can create ensembles for example, of many, many different protein-like things which have the same function, okay? And then we have enough data that we can start to use big data analysis to do statistical mechanics, okay? So that's the thing that we're quite excited about now. So let me just close by thanking the people who actually did the work. All I did was talk. And especially Sam Schoenholz and Dosh Trubuk, who Sam was a graduate student working with me using a much inferior method actually to try to find these defects. And Dosh Trubuk was a student of Tim Kaxiris at Harvard. Okay, they were friends from undergraduate days, and they were telling each other about what they were working on. And Dosh was using machine learning to do electronic structure, to do better than density functional methods for electronic structure, et cetera. And Sam thought, oh, I wonder if this is useful for my problem of finding, defects in glassy systems. And so they started working on it together. And they actually found that they could predict rearrangements with 90% accuracy before they even told me that. Okay, they really deserve a huge amount of credit for starting up this line of research in my group. Okay, so thanks very much for your attention.
Thank you, Andrea. I'm sure if we could all clap, then you would hear us all clapping. But I guess that's kind of hard in a webinar. But thank you. And so I guess the floor is open for questions. So if anyone has a question, you can look in the bottom of your screen. There's a little option to, oh, yes, just one second. All right. So there's an option in the bottom of your screen to raise your hand. If you raise your hand, then Andrea and I can see you and we can call on you. In the meantime, I have a number of questions that I can ask while people are thinking of theirs. So you're mentioning that what you learned with Carl is that you have to be able to design ensembles. I was kind of wondering what you meant by that. I mean, yeah.
What we learned with Carl is how to design ensembles. So,
Okay.
So the idea is this. So one of the things. Okay, so one of the things we've done is that Carl was involved with was to design. Oh, what happened here? Oh, how come I cannot? What happened here? What happened to my shared screen? I'm going to stop it and start it again.
Yeah, we had some blades of grass.
Oh, I know what I did. I just turned off the. I know what I did. Okay. Yeah. So what we did was, this is Jason Rox's first author, but Carl was involved in this, in figuring out how to do this at the very end of his PhD, which is, suppose you have a protein that has this function called allosterase, so that if something binds over here, then that changes the conformation of a protein over here so that it can or cannot bind something. And for example, if the protein is an enzyme, then suppose what needs to bind over here is some molecule that's going to get hydrolyzed or phosphorylated or something and then go off, some chemical change and then go off. But I can control whether that enzyme is on or off by having this thing over here bind. In mechanical terms, what we're doing is we're applying a strain here, and we want a comparable strain over here. And what we figured out was how to design mechanical networks to have that property. Okay, but the thing is that I can have many, many different mechanical networks that all have the same property. And so in order to understand how am I developing that property? That's a collective function. What are the microscopic changes as I design the system that are needed, the microscopic design rules that are needed in order to get that function? I need to design many, many, many different networks which have the same function, and then I can look and say, what do they have in common? What was important there? So that's the kind of ensemble thinking that you need if you're thinking about trying to do statistical mechanics, understand the microscopic basis of that collective function. And so we couldn't just rely on what comes from protein families across species, conserved amino acids and proteins. That's not enough.
It looks like we have a question from Herbert. I'll go ahead and allow him to talk. Hi, Herbert.
Hey, Scott.
Hi.
Hey, Andrea. I have a question in relation to your measuring the neighborhood of an atom, say.
Yes.
I'm sure you tried different versions and selected the ones that works best with a machine learning approach. I wonder whether the following modification of your measurement, how it performs, namely, when I measure the neighborhood, I also include their own softness measures of the neighbors in the computation. Does this change much, or what is the effect of that?
Yeah, we did play around with that. We were hoping that that would change things a lot. It doesn't change things that much. So it's very interesting. We've looked at lots of different kinds of structure functions, including softness itself of the neighbors, right? It's trying to do something in a iterative, sort of self-consistent way. And different ways of doing machine learning. We can never get much above 90% accuracy.
Yeah.
Okay. And that is interesting. I think there's physics there. And it could be that that's how much physics can be captured by any measurement of local structure.
My guess would have been that if you have a lot of soft neighbors, that maybe the probability of yourself changing is higher. That is, you have a higher derivative in the measurement.
We know it is because we know we've looked at the spatial correlations of softness.
Okay.
Okay, and they decay on the scale of the particle size.
Okay, thank you.
Yeah, so that does. But so, by the way, this 90% thing is at a certain temperature. What we do is we train at a hyperplane at a fairly low temperature where we can still get good statistics. Okay. And then we apply that hyperplane. So everything I was showing you as a function of temperature, we apply the same hyperplane at all the different temperatures. And what we see is that as we lower the temperature, okay, the accuracy actually goes up, so that in the aging systems at quite low temperature, the accuracy is more like 95%. So that's saying that some of that difference of the 90%, some of that 10% that we're missing comes about from thermal fluctuations. Okay, so that as the temperature goes down, it actually becomes more accurate. But the validation accuracy goes up. But some of it is probably beyond that, and is that thing that I said about local structure not capturing quite everything.
I actually have kind of a related question, which is, if you look at the slides you showed where you had several examples, including I think one on the right from Doug with
Yes.
dynamical heterogeneity.
Yeah.
I mean, that would kind of, to me, look like you have waves of softness. And I was wondering if you can think about it like that, and if so, then how I could set up maybe some kind of equation to get waves of softness. So I see these tracks of high mobility, basically.
Yes. So yes, we're exactly trying to understand that. So there's a postdoc, Rahul Chaco, who is working jointly with Giulio Biroli, Olivier Dochot, David Reichen, and me to try to understand that in supercooled liquids. I also have a postdoc, Gu Zheng, who's working with my student Sean Rideout and me, and where we're looking at a related problem but simpler. So the idea is you take a system of jammed particles, and you shear them quasi-statically, so infinitely slowly, very slowly, okay? And you can get avalanches there of motion, in other words, where one rearrangement triggers another, which is sort of like a kinetic heterogeneity that we're showing here. And you can look at the progression of that. And what we've been able to do is to look at the interplay of softness with rearrangements, the dynamics, with elasticity, and show how these things all affect each other to give that progression, that spatial sort of spreading of the motion that's similar to what you see in this movie. So yeah, that is an extremely interesting thing that we're working on.
Are there any more questions? Does anyone else have something they want to ask? Don't be shy. I actually had another one, which is, so we use machine learning to understand what parameters essentially lead to high mobility. And we get this thing, which is softness, which, I mean, I guess what I'm wondering is there an easier way to understand softness than just calculating with the computer, this is a soft particle, this is not. So, you're basically looking, I guess, at, weights in front of G of R. Is that kind of the basic idea? But then, are some weights so much more important than others, or are they all kind of equal scale? So you really can't say, any one thing is, I mean, I guess they probably decay as I go further away, for example.
No, that's right. So the most important one turns out to be, so we can look, you can do what's called recursive feature elimination, or you can just do it by hand and say, okay, what accuracy do I get if I just include this one or that one? Okay. And it turns out that if you just include the height of the first peak of G of R, so 50% of, accuracy would be just random guessing, okay? So I think you get to 67% just with the height of the first peak of G of R. And now if you take two things, the height of the first peak and the depth of the first valley, okay, you get up to something like 77%.
Okay.
Okay, so, and then it just gradually increases as you get more from there. So yeah, so it's really the height of the first peak, the depth of the first valley, the height of the next peak, okay, that you can do really well just with those. So you can reduce it from having 100 different dimensional space or 100 different structural variables. We can do almost the same validation accuracy with maybe 8 or 9, 8 or 10. Sorry, we always have an even number.
Okay. Well, there is one more question from Herbert's. Okay. Okay, Herbert.
Yeah, so this question relates to the first one you got from Matthijs, and your answer seemed to indicate that you are familiar with the work of Yoshito Hiraoka in Japan using persistent homology, and I'm curious of how
they applied it to silica, right?
Right.
That's the paper. Yeah.
Yeah.
I think I was actually a reviewer.
Okay.
Of their paper. Yeah.
How does your work relate to Hiraoka's work? Is there that there seemed to be a relationship and an overlap, but it's not clear to me how.
So what we're doing is we're going beyond that. So they used persistent homology, and they found that there were certain things that did tell you about the dynamics. What we're doing with the machine learning is we're saying, let's take several of those things and put them together, and a combination of those things, a linear combination of those, works even better. Okay, so for example, so we've done this for jam systems that are being quasi-static sheared. So we do the persistent homology analysis. And what comes out of it, it tells us, okay, that the most important, then we can look at basically birth-death persistence diagrams. and say, okay, what are the most important features here? Okay, and what we find is that, for example, if you take the number of interacting neighbors in your Voronoi cell and the number of neighbors in the Voronoi cell that are actually not interacting, that are not overlapping, not okay, just those two things, you actually do quite well in a jam system. And then if you include more, you do even better. So look at the next level of neighbors.
Yeah.
Yeah. So and so you can get this kind of thing. This is the kind of insight that you can use the persistent homology to find, and then you stick that insight to find structural a bunch of structural quantities. You can then construct linear combinations of those, and you can get away with many, many fewer structural quantities if you have that intuition going in.
So if I understand you right, what you're saying is that Hirooka used only the immediate neighbors because that's just how his setup is. But then he was sophisticated in studying it using persistent homology, versus you use large neighborhoods and get some statistical average of the large neighborhoods, and this way get more information through that. Is that about correct, what you said?
He could look at large neighborhoods, okay? So it's not the size of the neighborhood, it's the number of different quantities we're looking at. So the whole point of machine learning is to combine a number of different structural quantities.
Okay.
Okay. And to find the linear combination of those that is most predictive. And so you can use persistent homology as a tool to find good candidates for your structural quantities. Okay, and that's what he did. He used persistent homology to find, oh, here's a structural thing that seems to correlate. Okay.
Yeah.
But now we're taking it further. We're saying, okay, let me, from persistent homology, get a bunch of these things, which are the most informative, and now let me construct the linear combination of those quantities that really tells me about the dynamics.
Yeah, but you don't use persistent homology, actually.
Not in this case, no, but we have used it in another case. So
Okay.
it is a good way of coming up with structural variables that you feed into your machine learning, and we've done that. And if you do that, you can get away with far fewer structural variables. 2
Okay.
instead of 10, 8 to 10, which is really nice from a physics point of view.
Thank you.
Yeah.
Okay, we have a question from Miguel.
Hi. This was very interesting. I suppose the next step after getting those features reduced to a select few would try to explain why they work. So to try to find a theoretical explanation for why those features connect so well with macroscopic observations. I wonder if there is work in that direction already.
Well, so for this G of R stuff, right? I don't know if there's so much work, but it says, yeah, this is a way of quantifying the cage, which is an old idea that's been around for glassy systems for many, many decades, that there's a cage, but nobody knows what that cage means. This is a way to quantify that. Okay. So I think understanding why it works is, in that case, the intuition has been there for a long time. For the jam systems where I use the persistent homology thing, again, we know from jamming that the number of interacting neighbors is a really important quantity. And so locally, the number of interacting neighbors really does tell us about dynamics. And that's again, pretty clear. And the number of neighbors, Voronoi neighbors that are not overlapping, these are ones that could become neighbors, which we know is important in a rearrangement, that you go from being a neighbor to not being a neighbor, you know. So I think that intuition, again, we can understand physically why that is. But yeah, we've been, I should say, we've been content with that, and we haven't pushed it further to say, oh, is there some, more rigorous way to show, yeah, this is the right thing.
Thank you.
Okay, are there any more questions? Now is your chance, everybody. I don't see any hands going up, but I want to thank you again, Andrea. It seems to have gone really well doing the online version, and thank you everyone for coming. This should be online at some point, and I believe the events team will send an email about how to access it. Andrea, we have another meeting we'll have with you directly afterwards. You should have gotten a link, so we can do a little post catch-up. And thank you, everyone.
Oh, I'm supposed to do something else now?
Oh, we were just, well, apparently we cannot close this meeting and have us stay on, so I'll close the meeting and then we can.
Oh, okay, great.
Yeah, just.
Okay, so I'll check my email for that.
Yes, okay. So
Okay.
Thank you again. Thanks
All right.
everyone for coming, and take care. Stay safe.
Okay, thank you. Thanks
Yes.
again for the invitation to speak.
Our pleasure.